Morning. Let us start with the doping in semiconductors. We have discussed earlier that semiconductor differs from the metal or the insulator in the sense that the band gap in semiconductor is very low, unlike in insulator where the band gap is very high. So, let us quickly remember those things, that this is the band gap and this value is high for, this is the Eg, the band gap, it is high for insulator, and for semiconductor it is very low, sorry, for semiconductor it is very low, it is insulator and it is semiconductor, right. In semiconductor, the carrier transport is governed by both electrons and holes, unlike in metal where it is governed by only the electrons. There is no concept of hole in metals. So, if I write down the conductivity which is given by sigma, this is equals to n e mu. This is the normal expression or general expression for the conductivity, where n is the concentration of electrons, E the charge of electron, and mu is the mobility of electron, if we consider that it is a fully electron based system like metal. But for semiconductor it is not a fully electron based system. So, your nu sigma will be the concentration of electron, the charge of electron, the mobility of electron, plus the concentration of hole, the charge of hole, and the mobility of holes, right. Remember that this mu n is the mobility of electron and mu p is the mobility of holes, and E the charges are same for electrons and holes, it is 1.6 into 10 to the power minus 19 except the sign, right, and n is the concentration of electron, E is the concentration of holes. So, these electrons and holes are there in the semiconductor, right. Now, let us take an example that I have taken one silicon sample, and you know that the sample can be intrinsic, can be extrinsic. Please remember that for intrinsic sample, the number of electrons and the number of holes are equal. So, I can write here, you see, if the number of electrons and number of holes are equal, then this P becomes the number of electrons, say. Okay. So, this n and this n, because for intrinsic, remember, for intrinsic they are same, and if you replace that n by n suffix I, if you replace that concentration of electron or holes, because they are same, by Ni, I stands for the intrinsic, then you can write that it is equals to E Ni mu n plus mu p. Okay. So, for intrinsic Ni is the concentration, and if you consider that both electrons and holes are present, then n or p are there. For intrinsic semiconductor, this rho becomes, sorry, the sigma becomes, the conductivity becomes E Ni mu n plus mu p, right. Now, the question comes, how the conductivity of semiconductor can be increased? Is there any process using which we can enhance the conductivity of electrons? Yes, there is a process using which you can increase the conductivity of the semiconductor, and that process is known as the doping process, right. It is doping process. That is not possible for other kinds of materials. It is a unique feature of semiconductor material. Okay? And this doping is very interesting phenomena. At the end of the lecture, I shall show you that just if you replace 10 to the power 8 silicon atom by 1 arsenic or phosphorus atom. Remember, 10 to the power 8 silicon atom by 1 phosphorus or arsenic atom, the conductivity will increase by several order of magnitude. So, that is the unique feature of doping, that you can change the conductivity of the semiconducting material by the controlled manner of doping in the material. So, why we dope the sample? To increase its conductivity. Apart from that, there is other advantage of doping that we shall discuss today itself, right. Now, say you have a silicon sample, and if you look at the picture, you see that this is the two-dimensional diagram of silicon atomic arrangement inside the lattice. What is the valency of silicon? 4. So, you see that there are the nearest neighbors are 4 for one silicon. For one silicon, if you consider this silicon, then the nearest neighbors are 1, 2, 3, 4. So, they have perfectly formed a covalent kind of bonding in silicon. Okay? So, that is why normally at 0 T you will not find any conductivity in silicon as well, though it is a semiconducting material. Now, if you want to dope this silicon, what to do? What is the process? What is the physics of doping? How the doping is done? The process is, silicon has 4 electrons in the valence band. So, if you add some element or an element having valence electron 5, then what will happen? 4 out of those 5 valence electron will share, and remaining 1 will act as a free electron, thereby increasing the conductivity of the material. So, since silicon belongs to group 4, you need group 5 elements: arsenic, phosphorus, antimony, etc. They have all 5 electrons in their outermost shell. See, this is the antimony. This antimony has how many electrons in the outermost shell? 1, 2, 3, 4 and 5. That is applicable for antimony, arsenic and phosphorus. But for boron, aluminum and gallium, because they belong to group 3 of the periodic table, boron, aluminum, gallium, etc. The antimony is there, Sb. Okay. So, you see that for this boron, aluminum and gallium, there are 3 electrons in the outermost shell, right. So, this is the way using which you can dope silicon. Remember that now we are discussing the case of silicon. Either you use antimony or arsenic or phosphorus, or you use gallium, aluminum or boron, that is applicable for silicon only. Why? Because silicon has 4 valence electrons. So, either you have to dope it by 5 to get it N type, or you have to dope it by 3 to get it P type. That is not applicable for other materials, it is applicable for group 4 materials. In this technique you cannot dope gallium arsenide, in this technique you cannot dope indium phosphide or zinc oxide or gallium nitride, that is not possible. because the electrons are necessary for the increase in conductivity, and you have to introduce controlled manner of doping so that free electrons are there. Here in this slide you see that one silicon atom has been replaced by the phosphorus atom. So, 5 electrons of phosphorus, only out of 5 electrons 4 electrons have formed 4, right, and 1 electron, this is the electron which is free in the crystal lattice. So, this free electron will move throughout the crystal lattice, and if you impart electric field in it, then you can increase the drift velocity of that electron in a particular direction, because unless you give some electric field, as I have shown you in my last lecture, that they will move at random manner. Only if you get an appreciable amount of current by the motion of those electrons, you have to apply an electric field, and if you apply an electric field, these electrons will move in a proper direction and you will get a current out of it, thereby increasing the conductivity. Now, one phosphorus atom gave you 1 electron. If you dope 10 to the power 8, 10 to the power 5 or 10 to the power 18, then what will happen? You will get 10 to the power 18 numbers of electrons, 10 to the power 14 number of electrons. But one condition is there. The condition is the phosphorus or boron or aluminum, whatever be the dopant atom, let us call those atoms as the dopant atoms, because they are used for doping, they must be ionized. Without ionization, that 5th electron will not be available for as a free electron. So, you have to make it free from the phosphorus. For that you have to ionize it. When it will be ionized, then what will happen? The phosphorus atom will be positively charged ion. It will be positively charged ion, because the absence of electron means it is a positively charged. So, then it will be a positively charged ion and the electron will be released to the crystal lattice. Not at all temperatures all the atoms will be ionized, it is not possible. So, at 0 Kelvin, what will happen? Nothing will happen, since at that temperature no ionization will take place, right. How the ionization energy is calculated? Who can tell? Any idea? You should tell. No, how it is calculated? Basically from the hydrogen Bohr's model. You have told the right thing, but you should say the generalized thing, because this is not a atomic class. So, it is basically the material science class. So, I shall show you that by using the Bohr theory of hydrogen atom in the ground state, what he told, that for taking n equals to 1, you can calculate the binding energy of the atom for a particular crystal lattice, and that means that is the ionization energy. If you give that energy, it will liberate itself from the bonding of the host lattice, right. So, here who is the host lattice? Silicon is the host lattice and dopant is phosphorus. Here the picture is more clear, the same picture. Here the picture is more clear. You see that 1, 2, 3, 4, 5, 6, 7, 8, they form the bonding and the 5th electron is away. So, basically you need for 4 silicon atoms, you need 1 antimony atom. For 4 silicon atom you need one antimony atom or one phosphorus atom. Then after doping what will happen? After doping you see that here you can find this is the circles have been marked with positive sign, that means they are positively charged ion. Remember that these are the phosphorus or arsenic or antimony. So, when they have liberated one electron to the crystal lattice, they became ionized and positively charged obviously. So, this positively charged means it has liberated one electron. Take the case here, come here on the right side diagram. Here you see that this is the negatively charged ion. So, they are boron or gallium or aluminium, they are ready to accept. So, they are the acceptor atom ion in this case, and these circles are basically the holes, these circle basically the holes. Here, yes, this picture will show you that phenomena. You see that when silicon is doped with boron, boron has 3 electrons, silicon has 4 electrons, you have 7 electrons in this system, you need how many electrons? 8. So, you see that there is a vacancy 1, 2, 3, 4, 5, 6, 7 electrons are there and one circle is there, open circle, that is hole. So, electron from the adjacent atom will come to fill that hole, electron from any adjacent atom will come to fill that hole, there one hole will be created, then a neighboring electron come to occupy that hole. So, in that position one hole will be created. So, likewise there will be a movement of holes in p type material. So, we find that in n type material the main carrier is the electrons. Remember that for n type materials the majority carriers are the electrons. For p type material the majority carriers are the holes. So, that is why in semiconductor both the electrons and holes take part in the conduction mechanism. Now, you come to that equation where I have shown you what should be the conductivity in such case. You see that this is the conductivity sigma, it is equals to n e mu n. This mu n is the conductivity of the mobility of the electrons and this mu p is the mobility of the holes. This n and p are the concentration of electrons and holes respectively. So, now you cannot use this relation where sigma is n e mu. After doping you have to use this relation, but we can make some approximation as well. How we can make the approximation? Suppose there is a material, you have doped it n type, there is a material you have doped it n type. Okay. This n type material has both electrons and holes. You can tell me, sir, from where the holes are coming? Because one thing be sure that we have started with intrinsic materials. So, in intrinsic materials there are electrons as well as holes, or say you have formed one p-n junction. So, when you have formed one p-n junction, then there will be both electrons and holes in that system. So, they will coexist basically. We need almost in all electronic device we need the p-n junction, be it diode, transistor, FET, MOSFET, light emitting diode, laser diode, detectors, right. basically those are junction device. Basically p-n junctions are there, but in different forms. We shall discuss those things also. So, in a p-n junction, in a device, both the electrons and holes are there, but if the number of electrons is very greater than the number of holes, if the number of electrons is very greater than the number of holes, then sigma can be written as n e mu n. We can avoid the second term consisting of plus p mu p. Yes, we can avoid or you can neglect this term. This term we can neglect. Okay, this term we can neglect. Why? Because n is very greater than p. So, we can neglect, right. Suppose there is a material and you are adding conductivity for n type, that means you are doping it, say arsenic or phosphorus, with arsenic or phosphorus. There is a material you are doping with arsenic or phosphorus, then what will happen? Suppose there are 10 to the power 10 electrons were there and 10 to the power 10 holes are there. So, as soon as you start doping, what will happen? The holes will be compensated. Remember the term compensation. The holes will be compensated. That means, when there will be 10 to the power 8 electrons, so that 10 to the power 8 electrons will recombine with 10 to the power 8 holes. How many holes will be left? 10 to the power 2. Why 0? 10 to the power 10 holes were there. Okay? Yes. Now, if you add more 10 to the power 2 electrons, then it will be 0. So, there will be no holes at all in the system. That is known as compensation. You can change the conductivity even. You can start from p type, add on electrons, the holes will be compensated by the electrons, it will be neutral or intrinsic, and then it will change its conductivity. That means, if you can start from n, say there are 10 to the power 10 electrons, add p, that means holes. First, these 10 to the power 10 holes will be there. So, it will be neutral, and then say 10 to the power 14 holes, if you add, go on adding holes, from n type it will become p type. From n type it will become p type. So, compensation in semiconductors is possible. Sometimes you find that you are adding the impurity of a particular type, but you are not getting the desired result. What should be there if you add on n or electrons? What will happen? You can expect that the conductivity will increase because you are doping with n type, but your result does not show you that trend. That means what will happen? Basically, it is compensating. Some effect of compensation is taking place in the system, in the material. Then at one point of time you will see that the conductivity is changed to other type. If you started from p type, it will come to n type or the vice versa. So, compensation is there, right. So, one thing is that we can increase the conductivity by doping. Second thing is that if both the materials are there, both p and n type, so the conductivity will be given by both the electrons and holes. We have to calculate separately. any mu, p mu, etc. And if a particular type of material is say dominating in the system, n, if n is very greater than p, then we can neglect this term, or if p very greater than n, the sigma will be given by p e mu p, that is also there, right. So, depending on the number of electrons and holes, you can approximate your equation or expression. This is known as the approximation, right. Say there are 10 to the power 14 electrons and 10 to the power 6 holes. You can tell that, you can say that it is almost n type. So, you can avoid the second term, or say in a system there are 10 to the power 16 holes and 10 to the power 5 electrons, there also you can neglect the term containing electrons. Okay. So, majority carrier concepts are there. Which one is the majority carrier? Is it hole or is it electrons? If electrons are the majority carriers, then it is known as the n type material. If holes are the majority carriers, it is known as the p type material, right. Then another important thing is the degeneracy, degenerate or non-degenerate semiconductor.
In n-type semiconductor,
Yes.
number of electrons are greater than number of holes.
Yes.
And in the p-type semiconductor, number of holes are greater than number of electrons.
Yes.
But both are electrically neutral separately.
Both are
Electrically neutral.
which one?
N-type is separately electrically neutral.
N type is
Separately
no. Electrical neutral means what is that? What is there? If you I do not know whether you have performed that experiment, that when hot probe measurements are done carried out, or say Hall effect measurements are carried out, you will find that it is negative. It is negative.
N-type is negative.
Yes, that is positive. P type materials will show you the positive, N type materials will show you the negative. Okay. Now, another thing is that the degenerate and non-degenerate semiconductor, what are those? One is degenerate, another is non-degenerate. Degenerate and non-degenerate are that, in my last lecture we have introduced one concept of density of states. We shall use today also in my second lecture. Density of states is a concept where you can get the number of available states for electrons or holes in the material. Let us see that there are two bands. So, in this band how many number of states levels are there? In this band how many levels or states are there? When we talk about the levels or states, it is basically the energy levels. It is characterized by a particular energy, x electron volt from the bottom of the conduction band, y electron volt from the top of the valence band, right. So, these states means say it is x1 from the bottom of the conduction band, say this is x2, it is bottom of the conduction band, it is x3, it is bottom of the conduction band, all those are in electron volt. Basically, those are energy. States means here the energy, the levels where electrons can occupy in the conduction band or the holes can occupy in the valence band. Similarly, there are states in the valence band as well. So, number of states is known as the density of states. Number of states means how many, yes, how many levels are there. Levels means where the electrons or holes can be accommodated, right, where the electrons and holes can be accommodated, and you can measure it by electron volt, and they are very closely spaced. I have shown you that there is a finite gap in it, but since there are 10 to the power 18, 10 to the power 14, 10 to the power 17 states are there. So, you can imagine that they are very much close to each other, that is why they form a band. For all practical purpose they form a band very close to each other x plus delta x, E plus delta E likewise. Yes, I am not going to discuss the quantum mechanics because this is a general material science class. So, only the concept or the phenomena will be discussed, and if someone is interested how those things happen, then we can make some calculation, but not in this class, that is not possible also. I can give you the reference, etc. Okay. So, number of states are there, and this number of states are different for different materials. It depends on the temperature and band gap of the material. It depends on the temperature as well as the band gap of the material. Now, what is non-degenerate semiconductor? Non-degenerate semiconductor is that where the Fermi level, non-degenerate semiconductor, if the electron concentration in the conduction band is much lower than the density of states, or hole concentration in the valence band is much lower than the density of states in the valence band, right. Then we can say that the semiconductor is non-degenerate, non-degenerate. Okay. Now, you can tell me that what is the value of the density of states? What is the value of density of states? It is different. In conduction band the value is say x, in valence band the value is say y, etc. But whatever be the value for a particular material, if the number of electrons in the conduction band is less than the density of states, then you can say that it is non-degenerate semiconductor. Okay. And that means the rooms are more than the guest in a hotel, say. The rooms are more than the guest in a hotel, say. Then you can say that it is a non-degenerate case. And if it is greater than the density of states, if the number of electrons and holes are almost equal to or greater than, but chance of greater than is not possible, because if there is no level, electron cannot move there. So physically it is not correct to say that if it is greater than the density of states, not that, but if it is comparable with the density of states, then it is known as the degenerate semiconductor. We shall deduce some expression, some relations of the current transport, etc., the calculation of the electrons and holes in the conduction band or the valence band. These are valid for non-degenerate semiconductor, remember, those are valid for non-degenerate semiconductor. For degenerate semiconductor, what happens? For degenerate semiconductors, the band gap reduces, there is a shrinkage of band gap, and delta Eg, that means reduction in band gap, it is given by 22 into n 10 to the power of 18 to the power half milli electron volt. It is for silicon at 300 K. Okay. This is the reduction in band gap, delta Eg is the reduction in band gap, and n is the number of electrons or holes in the respective band. And I can show you that for Nd less than equals to 10 to the power 18 centimeter cube inverse, delta Eg is less than equals to 0.022 electron volt. What is Nd? Yes, Nd is the doping concentration, that means we have doped silicon with 10 to the power 18 dopant atoms. So, that 10 to the power 18 is the doping concentration, 10 to the power 18 is the doping concentration. So, if it is less than equals to 10 to the power 18, then we see that delta Eg, that means the reduction in band gap will be less than equals to 0.022 electron volt, and it is almost 2%. What is the band gap of silicon? 1.12 electron volt. So, it is almost 2% of the original band gap of silicon at room temperature. So, it is not very high, but for Nd greater than equals to Nc, that means the density of states, the value is 2.86 into 10 to the power 19 centimeter cube inverse. This delta Eg is greater than equals to 0.12 electron volt. Okay. Two cases I have shown you. One is if it is less than 10 to the power 18, it is 0.22 electron volt, this is non-degenerate. But if it becomes greater than or equals to 2.86 into 10 to the power 19, then what will happen? It will be greater than equals to 0.12 electron volt. What it means? It is almost greater than 10% of the band gap, 0.12 electron volt. If the band gap is 1.12 electron volt, then 0.12 electron is almost 10%. So, it even if greater, that means it can be higher than 10%, the band gap is reduced. So, the original band gap can be reduced from 1.12 to 1 electron volt in this case, or even less. So, there will be a shrinkage of band gap. So, a material is characterized by its band gap. If band gap changes, then a lot of phenomena will be there, right. You are expecting that silicon will give this property, but it will not give because the band gap is changed. So, a lot of phenomena will be there. And another thing is that generally the carriers, that means the electrons or holes, when move from the valence band to the conduction band, this thing we have discussed earlier, that it moves from valence band to conduction band, right. Sometimes in degenerate semiconductors already there will be carriers in the conduction band, already there will be carrier in the conduction band, right, because the doping is so high that internally they will move from the valence band to the conduction band. So, your starting material will show you some metallic type of conductivity, because already there are free electrons in the conduction band. Okay. So, till now some terminology we have learned. One is that doping, second thing is intrinsic and extrinsic semiconductor, third one is N type and P type, fourth one is degenerate and non-degenerate semiconductors. So, the knowledge of these things we shall we can use when we shall discuss about the crystal growth and characterization and the device application, because our ultimate aim is to study the application of semiconductor materials in device or electronic materials in various kinds of device. Okay. So, first say 10 lectures we shall discuss the general type of thing, and the other lectures after 10 lectures we shall actually go inside the subject, where we shall synthesize the material, new and newer materials we can grow, various kinds of materials, their characteristics. Not that only the silicon or the gallium arsenide are the main semiconductor, not that. Obviously, sure they are the main semiconductors, but apart from silicon and gallium arsenide there are other several kinds of semiconductors for different kinds of application. So, it is there. Okay. So, now let us consider here, you see that after doping what happens, these are the holes and these are the electrons. So, there will be free electrons, and here if you apply a current or a, say you apply a voltage, that means electric field, here see you have applied a voltage and this is the positive terminal of the battery, this is the negative terminal of the battery. So, there will be a flow of current from where? In the opposite direction, the electron moves in the opposite direction. Okay. So, that is very important thing, that you see that the electrons move in this direction. So, the current will be from the positive polarity to negative polarity. Okay. Here see the electrons move from negative to positive, right, because the electrons will move in the direction of the right, and so the conventional current will be opposite to the direction of the electron flow. Okay. So, these things we have discussed. Now, another important thing is the intrinsic level EI. EI is the intrinsic level. What is intrinsic level? Intrinsic level is an imaginary electron state or imaginary level inside the band gap, which is almost half away from the bottom of the conduction band or the top of the valence band, and it is applicable for intrinsic materials only, where the number of electrons and number of holes are equal. Okay. So, intrinsic level is applicable for the intrinsic materials, not for doped material, remember. For doped material, the level is denoted by the Fermi level. We shall discuss today the details of Fermi level in the next lecture. Okay. So, you see that this is the intrinsic level, and this intrinsic level is basically the halfway between, suppose this is EC and this is EV. What is EC? EC is the bottom of the conduction band, remember. That means, if you consider that the band is parabolic in nature, so it is the bottom line. Similarly, EV is the top of the valence band, and the difference is for silicon is 1.12 electron volt. So, that will give you the band gap. Now, if it is intrinsic silicon, say this is intrinsic silicon, then what will happen? There will be a level which is denoted by EI, and this level is halfway. That means, if you divide 1.12 by 2, 1.12 by 2, what will happen? What is the value? 0.56. So, it is 0.56 electron volt almost, and it is 0.56 electron volt almost halfway between the two band edges, that is the band edge, BAND EDGE. EC is the conduction bandage, EV is the valence bandage. This is the bandage, conduction bandage, and this is the, there is conduction bandage, this is valence bandage. Okay. So, halfway between the bandages there will be an intrinsic level, and that is applicable for intrinsic materials. Okay. What is the intrinsic carrier concentration of silicon? Can you say? What is the intrinsic carrier concentration of silicon? It is 1.45 into 10 to the power how much? No, it is 10 to the power 10. Okay, centimeter cube inverse, or in some books you will find that it is 1.5 into 10 to the power 10. Intrinsic carrier concentration, that means in the material 10 to the power 10 electrons and 10 to the power 10 holes are there. Okay. 10 to the power 10 electrons and 10 to the power 10 holes are there. That is the intrinsic carrier concentration. It is different for different semiconductors. For germanium it is 10 to the power 13. For gallium arsenide it is 10 to the power 6. I shall show you the value in the next lecture. Okay. So, this is the schematic bond pictures for N type silicon. Here we have used the arsenic as a donor, and here the boron, and already we have shown, already we have seen that this is the free electron, or this is the hole which is to be filled by the adjacent electron. So, when this electron will move here, there will be a hole created here, then this electron will move here to fill that hole. So, there will be a hole here. So, there will be a hole transport in the material for p type semiconductor. Okay. So, with this I conclude that there will be doping in the material, and the doping basically changes the conductivity of the semiconductor. It can cause other enhancement of the properties also, as we shall show you in the next lecture, and some of the terms we have introduced which we shall discuss in detail in the next lecture. So, there will be a break for some 2-3 minutes, then we shall assemble and we shall start. Okay. Thank you.